Now, along with that, of course, you got in. So we've discussed nodes, we've discussed topics, we've discussed a whole lot of things. There are services which are available as a request response basis. So they run in the background, they're not a part of this communication framework. You send them a request and they'll send you a response as any services, as any web services. You've got a parameter server. So sometimes what happens is you've got constants. So you can hard code them into the program, but then if you have to change these programs, then every change means you need to recompile the program, reinstall the program. We are talking about software suites, and then run the program again. So the easier way is to do it using a centralized parameter server. So what the parameter server does, it's a server, it makes a list of all parameters, its current values. And by calling in certain requests, you can update its values or you can get its current value. So in your programming scripts, all constant, you just access a parameter server to get the current values, and these values can be verified without the need to compile and install this thing. And that's how we handle all parameters. It actually becomes very important because you know from research, a lot of efforts are spent towards parameter optimization. And remember that every parameter, if you need to recompile your program, you can do it right now. Many of you do it. Reinstall the software suite, which is your program only, and then rerun it up. It takes a long time. What if I could do it on the fly by giving it commands to the parameter server and just rerun it? So that's something amazing that ROS does provide. Okay, next, what we need to study is that as of now, we said that there will be a pause, which will mean a topic pause. So the localization system will write on the topic pause, and of course, the planner will read from it. Now, the problem is that I have 10 robots, and of course, each one of them has a different pose. And if all of them, so there are 10 localization systems, one for each robot, and if each one of them writes to pose, then there's a problem. And that's a problem that has already been seen into software where different functions could have different names, and the answer is, of course, what is called as namespaces. Now, I'm not looking at namespaces because ultimately ROS programs are also Python or C++, so those namespaces obviously hold. I'm looking at the namespaces of the communication mechanism. So the namespaces of the communication mechanism, which is basically these topics, come in the name of so that's the outer namespace, that's the outermost namespace, that's the actual variable name or the actual topic name. This is the inner one, this is the slightly outer one, that's a slightly outer one. So the namespaces are in a hierarchical manner. Just like in C++, Java, Python, you can have namespaces at any level of hierarchy. Now, what that means is that if I'm referring to robot 1, my namespaces will be called as like this. And if I'm doing it for robot 2, it'll be called as this. And my variable naming conflict is absolutely solved. So now let's look at a problem we'll also practically see. Let's talk about any one module. Let's talk about controller. So let's say that I have localization 1. That's my localization program for the first robot. It writes to /r1/pose. I've handled the namespaces perfectly, and there's a control one that controls robot one. It looks at all /r1/pose, and it also looks at /r1/goal, and it tries to make the robot reach that goal. Simple enough. Now, I also have a second controller, and that's just a PID controller. Let's have the second robot as well. Now, it can be done, so there's absolutely no problem. But then, topic names are just variable names. It's just a channel over which communication goes. But these are physical code. So these are Python, C++ files, which have lots of lines of codes. And the moment I'm talking about physical real codes, you know, there are maintenance issues, there are documentation issues, there are everything. Now, a PID controller should be the PID controller, and the only change is in the inputs. That's the only change. Everything else remains the same. So there should be a way to call this controller in a way that it takes either this inputs or it takes this input, so that I have only one PID controller for n robots, and that's valid for the kind of simulations, especially concerning swarms, that we are doing. We are doing some swarm behaviors that now we expect to do using ROS. And if every robot has its own controller, then we are talking about too many files. So far, we just had one controller, and by changing the parameters in a loop, we could control all the robots by using one control algorithm alone. So one of the ways to handle this is what's called as remapping. If I physically look at the control code of this one, and if I look at the control of this one, the only change is wherever within strings you have /r1/pose, that gets converted to /r2/pose, and wherever I have /r2/goal, that gets converted into /r2/r1goal, it gets converted to /r2/goal. So what I can actually do is, while running this program, using a way we'll see it in practice, while running this program, I can say run controller and change /r1/pose to /r2/pose, and change /r1/goal to /r2/goal. So what this does is that it kind of goes into the program, it changes all this to this, and then it runs it. That's not exactly what happens. It actually tells remember, everything was being registered with the event manager. So it tells the event manager that in this program, instead of directing packets of this channel, you instead redirect packets of this channel, and instead of writing to this channel, this topic will write to that channel, and that's all. So that's one thing that I can do. I can always do this remapping, which is how I run the program. I can tell that there's only one controller and just the inputs are coming from a different channel. Now, in reality, we talked about many scripts, one for every module, and one for every robot, and one for fans, and one for everything. So there are too many scripts. Now, if you keep on running that in terminal, it will take too much amount of time. So we'll invoke the motors, we'll invoke the first sensor, second sensor, third sensor, robot 1, robot 2. We'll just be invoking robots. We want to do it as a together. You could say that write down a script for it, but these are programs which are infinite. Every script is an infinite loop. So that's not how script works. A bash script or a shell script, it gives the first thing as input and then it waits for that to terminate before it goes on to the second line. So the first program will never execute. Each one of these is an infinite script. Simulation runs till eternity, and therefore we call as a launch file. So a launch file is a list of all nodes to be executed. So launch file is a list of all nodes to be executed, along with some of them may have arguments. You've seen command line arguments in C++ also. You can say program name and then the arguments, and those go as argc and argv. So here, of course, there's a more advanced argument control. So you can have arguments in your script and you can specify that either using launch file or using control like this, remappings, and other parameters as may be necessary. So that's exactly what I do. I will write down many scripts. We'll see it as a part of the laboratory courses, as a part of laboratory exercises. And once we do that as a part of the laboratory courses, we'll see that you'll also have to write down multiple robots. And of course, you'll not show me the output by running each one of these robots separately. All that you might prefer doing is to just write down a launch file, and the launch file, it invokes all the robots up at a single time.